You turn on the tap and clean water flows out. Clear, tasteless, safe to drink. For most people, this feels completely normal. Yet drinking water is not a natural product. It is the result of one of the most strictly controlled and technologically demanding processes modern society operates every single day. If this system stopped working, cities would begin to fail within hours. The first thing to understand is simple and uncomfortable. Natural water is not drinking water. Rivers, lakes, reservoirs, and even groundwater contain bacteria, viruses, parasites, heavy metals, nitrates, pesticides, and microscopic contaminants that cannot be seen with the naked eye. Water can look perfectly clean and still be dangerous. Appearance means nothing. Drinking water production does not start in your kitchen, and it does not start with a household filter. It starts with the selection of a water source. This decision determines how complex the entire treatment process will be and how stable the water quality can remain over time. Surface water and groundwater behave very differently, carry different risks, and require different treatment strategies. If you like similar educational content, please like, subscribe, and share the video with your friends. Once water is taken from nature, it enters a world governed by physics, chemistry, and microbiology. A water treatment plant is not a single filter or a simple machine. It is a carefully connected chain of processes where every step depends on the previous one working correctly. Water is cleaned, clarified, disinfected, and finally stabilized, so it remains safe not only at the plant, but throughout its entire journey to homes and businesses. Here comes a crucial paradox. The goal is not to make water sterile. Sterile water would be chemically aggressive, unstable, and damaging to pipes and infrastructure. The goal is microbiologically safe water that meets strict health limits, tastes natural, and remains stable inside the distribution network for hours or even days. Every part of this process is continuously monitored. Chemical composition, microbial content, turbidity, pH, and disinfectant levels are checked around the clock. Drinking water is one of the most controlled products humanity produces. And yet, most people never think about it until something goes wrong. In this video, we will break down how drinking water is produced without simplifications and without repetition. From water sources and early treatment stages to advanced purification, disinfection, and distribution. Because once you understand what it takes to turn raw natural water into safe drinking water, you will never look at a simple glass of water the same way again. Every drop of drinking water begins its journey in the natural environment, and the type of water source determines almost everything that follows. There is no universal solution. What works for one region may be inefficient, risky, or economically impossible for another. That is why water treatment always starts with understanding the source itself. Water sources are generally divided into surface water and groundwater. Surface water comes from rivers, lakes, and reservoirs. It is relatively easy to access but highly variable. Its quality changes with rainfall, snowmelt, agricultural runoff, industrial activity, and seasonal biological processes. After heavy rain, surface water can become cloudy, rich in organic matter, microorganisms, and contaminants washed in from large catchment areas. Because of this instability, surface water requires the most complex and multi-stage treatment. Groundwater behaves very differently. As it slowly moves through soil and rock layers, it undergoes natural filtration. This often makes it clear and low in pathogens. However, clarity does not equal safety. Groundwater may contain dissolved iron, manganese, arsenic, nitrates, or have unsuitable pH and hardness. Treating groundwater usually focuses less on removing particles and more on chemical correction and stabilization. Once a source is selected, water intake begins. Water is collected through intake structures, wells, or infiltration systems, and transported to a treatment plant. From this moment on, the water leaves the natural system and enters a fully controlled technological process. Monitoring starts immediately. Parameters such as temperature, turbidity, conductivity, and basic chemical indicators are continuously measured to detect sudden changes in quality. The first goal of a treatment plant is not perfect purification. It is system protection and stabilization. Raw water first passes through screens, grates, or coarse filters that remove large debris such as branches, leaves, sand, plastics, and stones. This step may look simple, but it is essential. Without it, downstream equipment would suffer damage, blockages, or rapid wear. After coarse removal, the water enters pre-treatment. For surface water, this often includes aeration or pre-oxidation. Aeration introduces oxygen, helping to release unwanted gases, reduce odors, and partially break down organic compounds. Pre-oxidation can also improve the efficiency of later chemical processes and reduce taste and odor problems before they become harder to remove. Another critical function of this stage is flow and quality equalization. Treatment plants cannot operate effectively under sudden fluctuations. Raw water may be temporarily stored in balancing tanks or reservoirs where it mixes and stabilizes. This prevents sharp changes in turbidity or chemistry from disrupting the next stages of treatment. Even at this early point, the process is already highly controlled. Continuous measurements ensure that abnormal conditions are detected before they can affect the core purification steps. If something goes wrong later in the process, the consequences are far more serious and harder to correct. This stage reveals an important truth. Drinking water production is not about a single powerful technology. It is about a chain of carefully coordinated steps, each preparing the water for the next. If the early stages fail, no advanced filtration or disinfection can fully compensate. Once raw water has been stabilized and pre-treated, the process reaches its most critical turning point. This is where the majority of dangerous contaminants are actually removed, even though they are completely invisible to the human eye. And this is also where one of the most counterintuitive steps occurs. To clean water, chemicals must be deliberately added to it. Most impurities in water are not large particles that can simply settle or be trapped by a filter. They exist as microscopic colloids, bacteria, fragments of organic matter, and dissolved compounds. These particles are so small that gravity has almost no effect on them. They remain suspended because they carry electrical charges that cause them to repel one another. The first step in breaking this stability is coagulation. A coagulant, typically based on aluminum or iron salts, is carefully dosed into the water. Its role is to neutralize the electrical charges on suspended particles. Once these charges are disrupted, the particles lose their ability to repel each other. This moment is crucial. Without it, no further physical removal would be possible. Immediately after coagulation comes flocculation. The water is gently mixed at controlled speeds, allowing destabilized particles to collide and stick together. Over time, they form larger structures called flocks. These flocks are no longer microscopic. They are heavy and visible enough to be physically separated from the water. The mixing must be precise. Too strong and the flocks break apart. Too weak and they never form properly. Once flocks are formed, they must be removed. This is done through sedimentation or flotation. During sedimentation, flocks sink to the bottom of large basins under their own weight. During flotation, tiny air bubbles attach to the flocks and lift them to the surface, where they are skimmed off. The choice between these methods depends on water temperature, density, and the nature of the contaminants. The goal is always the same: remove as much unwanted material as possible before filtration. After this separation, the water enters filtration, which many people mistakenly believe is the main cleaning step. In reality, filtration works effectively only because coagulation and flocculation have already done the hard work. Treatment plants use multi-layer filters made of sand, anthracite, or granular activated carbon. Water flows slowly through these layers, allowing remaining fine particles to be captured deep within the filter bed. Activated carbon plays a special role. It absorbs organic compounds, pesticides, pharmaceutical residues, and substances responsible for taste and odor. By the end of filtration, the water appears perfectly clean, clear, colorless, and visually pure. Yet despite its appearance, the water is still not safe to drink. Microorganisms such as bacteria and viruses may still be present. Filtration removes particles, not biological threats. This stage prepares the water for the final and most sensitive process. Without proper filtration, that final step would be unreliable and ineffective. This part of the process shows how tightly chemistry and physics are intertwined. Every dose, every mixing speed, and every contact time matters. There is no room for guesswork. Drinking water quality is the result of hundreds of precisely controlled decisions, all of which must work together. After coagulation, flocculation, and filtration, the water looks perfect. It is clear, odorless, and free of visible impurities. Yet at this stage, it is still not fully safe to drink. Harmful bacteria, viruses, and microorganisms may remain. The final and most sensitive stage of drinking water production is therefore disinfection. The purpose of disinfection is not sterilization. Sterile water would be chemically unstable and aggressive toward pipes, valves, and household plumbing. Instead, the goal is microbiological safety, eliminating pathogens while maintaining chemical balance and long-term stability. The most widely used method is chlorination or chloramination. Chlorine is effective, fast, and crucially leaves behind a small residual concentration. This residual disinfectant continues to protect the water as it travels through kilometers of distribution pipes. Without this protective effect, water could become contaminated again long before it reaches consumers. Some systems also use ozone or ultraviolet radiation. Ozone is a powerful oxidant that destroys microorganisms and organic compounds, while UV light effectively inactivates bacteria and viruses without adding chemicals. However, neither ozone nor UV provides lasting protection in the distribution network. For this reason, they are often combined with low-level chlorination to ensure safety beyond the treatment plant. After disinfection comes water stabilization. Parameters such as pH, hardness, and mineral content are adjusted. Water must not be too acidic or too soft. Aggressive water can corrode pipes and leach metals into the supply. Overly hard water causes scaling and operational problems. Stabilization ensures that water remains compatible with infrastructure and pleasant for everyday use. Only after this adjustment does drinking water enter the distribution system. But control does not end there. Water quality is continuously monitored throughout the network. Samples are taken at multiple locations to check disinfectant levels, chemical composition, and microbiological safety. The system operates continuously, day and night, without interruption. One of the greatest paradoxes of drinking water is that it must remain alive. It must contain minerals, maintain balance, and remain chemically stable. Water that is too pure becomes aggressive. Water that is too natural becomes dangerous. Drinking water is therefore a precise compromise between safety, stability, and usability. The entire process operates silently in the background of modern life. We rarely notice it, yet it is one of the most critical systems supporting civilization. Without it, cities could not function, health systems would collapse, and daily life would come to a halt. Tap water is not a gift of nature. It is the result of advanced technology, physics, chemistry, and biology working together every single day. And that is why a simple glass of drinking water is one of the most remarkable achievements of modern society.